Hello and welcome to another video. In this video we're going to be working on power of 2, and in the problem you're given an integer n and you want to return true if it's a power of 2, otherwise return false. An integer is a power of 2 if there exists an integer x such that 2 to the x equals n. So for 1 it's true because 2 to the 0 equals 1. For 16 it's true because 2 to the 4 equals 16. And for 3 it's false, there's nothing. So one thing we know right away is if n is less than or equal to 0, then this is false. Because we can't get 0 with a power of 2, like 0 isn't a power of 2. We also can't get negative numbers. Because 2 to a positive number, like 1 or whatever, will be positive, and 2 to a negative number, let's say negative 3, is the same as just 1 over 2 to the 3. So it will just be fractional. So we can't get negative numbers here, so if our number is negative, we can just return false. And so let's talk about a few ways of doing this. So one way is you can just go through all powers of 2. So you can say like, okay, I'll just start at 1, which is 2 to 0, and then I'll multiply by 2, and I'll keep going and multiplying by 2 until I either hit my number or I pass it. If I pass my number, then my number is not a power of 2, and if I hit my number, then it is. So for example, for 16, we'd say like, okay, we have 2, it's still less than 16, so let's multiply again. 4, still less than 16, multiply by 2, 8, still less than 16, multiply by 2, get 16. And then let's say our number was like 33 or something, we'd kind of do the same thing. So we would keep going, we would multiply by 2, get 32, multiply by 2, get 64, and then we say, okay, we passed our number, so our number is not a power of 2. That's one way. Another way is you can actually just do a log, like you can just calculate log base 2 of the number, and it will just give you, like, you just check, is it a whole number or not? Another way is you take your number, so let's say we have 16, and you just keep dividing by 2 until you hit 1. And if you hit 1 and every single intermediate result was even, then it will also be a power of 2. So we can say like 16 divided by 2 is 8, that's even, so let's divide by 2 again, that's 4, that's even. Let's divide by 2 again, that's 2, that's even, and then let's divide by 2 again and get 1. So we got down to 2 to the 0, and then every number bigger than 2 to the 0 has to be even. So if you get a fraction or anything, then you know you failed. So that's another way. And so one more way is, before we actually talk about like the best way that's kind of tricky, is bit manipulation. So every power of 2 has one 1-bit and all zeros. So if we take a look at like how is 1 represented, 1 is represented like this with a bunch of zeros. 2 is represented like this. 4 is represented like this. 8 is represented like this, and so on, right? You basically just keep moving this 1-bit farther and further down, and that gives you a new power of 2. So because you know your number only has one 1-bit, you can just keep checking the last bit of your number. So we can say like, okay, let's just check the last bit of our number, and anytime we hit a 1, we can get rid of the bit. So we're going to keep deleting the last bit, right? So let's just walk through an example. Let's say our number is 33. So 33 is 32 plus 1. Or let's use a smaller number just to make it easier. Let's say our number is like 9. So it's 8 plus 1. So 8 is this over here, and 1 is over here. So we can just say like, okay, let's just AND our number with 1. And if we get a 1, we will, no matter what we get, so let's AND our number with 1, take the result, and then get rid of the rightmost bit by shifting it to the right or dividing by 2. So we AND it with a 1, we get rid of this rightmost bit. Then we check, did we get a 1? And if we got a 1, this has to be 0. Because since a power of 2 only has one 1-bit, anytime you find it and you get rid of it, the rest of the number has to be 0. So that's kind of the idea. So here we said, yes, this is a 1, but this is non-zero, so this is not a power of 2. And then for something like 8 or 16, let's say this would work, right? So for 16, it would be this, I think, right? So 2, 4, so yeah, it would be this right here. So what would happen here is we would AND it with a 1, we would get 0, get rid of the last bit. This was 0, so we keep going. AND it with a 1, get 0, keep going. AND it with a 1, get 0, keep going. AND it with a 1, get 0, keep going. AND it with a 1, get 1. But now we get rid of this bit, so now our number is 0, and then we'll say, oh, we did find the 1, but now our number is 0, so this was a power of 2. So for 16, it would just work. And all these ways work. And now let's talk about the optimized way to do this. So you do have to know that thing that I said, that for a power of 2, you only have 1, 1, and all zeros. So that's going to be relevant. So let's look at some other numbers to find another thing that's relevant. And I'll briefly talk about how this works. And I didn't come up with this myself. I think it's pretty hard to come up with, to be honest. But once you see it, it kind of makes sense. So the representation for negative numbers in binary is with 2's complement. It's pretty straightforward. Like, let's say we have this number, doesn't matter the number, represented in binary. What you do is you invert every single bit. So you invert every single bit like this, and then you add 1 to the last bit here. So you would add a 1. So this would become 0. This would become 0. And then this would become a 1, right? Just basic bit addition. So now what happens is, here is our positive number, here is our negative number in 2's complement. And if you AND these together, you will get all zeros and a 1 in the rightmost bit of the original number that was a 1. So you will get all zeros, so it'll be like 0, 0, like we can even write it, 0, 0, 0, 0, 0. And this is going to be a 1. And then for a power of 2, this is going to equal that power of 2, right? You only get 1 bit, but for a power of 2, the rightmost. So the other thing is, when you do this, the rightmost 1 bit of the original number will be preserved. So you can see, like, here's the original number, here's all the bits. The rightmost 1 bit is over here, and it is preserved. And because a power of 2 only has 1 bit, you will basically get the same number that you started with. So when you do this, when you get the positive number and the negative number, you will get the original number. So you can just check, like, okay, if I do 4 and bitwise and -4, I should get 4 here. That's the idea. So we can look at another example here. So these aren't power of 2's, so that's why this is not going to work, right? Like, this number is not the same as our original number here. So let's take a look at another example. So this is the same thing, just a different number. This is it reversed, right? So this is the positive number, this is the negative number. Now remember, we have to add 1 to the last bit to do 2's complement. So basically this is going to be a 0. Now this will carry the 1, carry the 1, carry the 1. This will turn into a 1. Then when we AND both of these together, we get 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, which is not the same as our original number. So let me briefly explain why doing this like number and the negative number works. So if you take a look at the number, like, let's go back. So here's our number before adding the 1. Basically what's going to happen is, for any number, when you reverse the bits, all of the bits to the right of the rightmost 1 will become 1s. And that 1 will become a 0. So you can see, like, the rightmost 1 becomes a 0. We can even look here as well. So we can go back before we did, like, all our reversing. So let's go back. I think this is good. So let's look at both of these numbers. So you can see, like, for this number, all of the bits before this number are going to be 1s, and then this will be a 0. So basically, it's kind of the same thing as having, like, this location. Like, if you think about it in decimal, this location will turn into a 0, and in decimal, every number before this will basically turn into a 9. So then when you add the 1, these will all become 0, 0, 0, and then this will be a 1. So that's why the rightmost bit gets preserved. So you could see, like, here, this becomes a 0, and every number before this turns into a 1. So when you add the 1, everything to the right of this rightmost 1 will be 0, and then this will be a 1. Same thing here. The rightmost 1 is here. So every number before this will be a 1, and then when you add 1, all of these will turn to 0, and then this will be a 1. So that's why that always happens, is in 2's complement, the rightmost bit gets preserved, and then the rest of them get changed. So you could see that. And so let's take a look at what happens with a power of 2. Like, this is actually a power of 2. This is 16. So here's our positive 16. Here's our negative 16 before adding the 1. So same kind of thing. Our rightmost bit is over here. So when we do the 2's complement, every bit will be negative. So when we add 1, then this every bit will become 0 up until the rightmost bit, and then the rightmost bit will become a 1 again. So when we AND these together, we will get 16 again, because you will get 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, which is our original number. So that's why that works, and that's kind of like the trick. So essentially you can just say, okay, if our number is less than or equal to 0, false. Otherwise, let's do the number and, bitwise and, negative number. And if this is the same as our number, then we want to return true because it is a power of 2. That's kind of the trick for it. So let's code that up. And I'll briefly show the bitwise solution as well. So the one that I was talking about, where you just check for a power of 2, and if you find it, then you check is the rest of your number 0. So we can do that as well. So we can say like while n is, so first we can say if n is less than or equal to 0, just return false right away, because like this can't happen. Then we could say while n is greater than 0, we can say like our last bit or something equals n and 1. So that'll give us our last bit, if it's a 1 or not. Then we can shift it to the left or to the right, right? So this will just get rid of the rightmost bit. And then we can say if n is non-zero and last bit is on, that means this can't be a power of 2 because this has more than one bit. So we can say return false here. Otherwise, we can return true if we manage to go through our whole number and we only found one bit. So we can submit, and you can see this works. And the fast solution that I showed in the examples, where you just do and, you can do this. You can say return n and negative n. And like I said, because the way this works is, oh, I still need this part here. What am I doing? Oh, right, forgot one more thing. It needs to equal n. Okay, hopefully that's correct. Yeah. And as far as the runtimes, it's not super important. Like even though loop or the recursive solution, going through bits of a number or dividing a number by 2 is a log n problem. So this will take like 30 operations or 20 operations total. So really, no matter what you do, it'll be super fast. So this time isn't going to be like super accurate. But yeah, essentially, this is kind of a cool trick to know is, yeah, because when you do a n and negative n, you will basically just only preserve the rightmost bit, because a two's complement number, the rightmost bit will stay the same and every other bit will be different. From the left anyway. So that is, like I said, once you kind of see these, it makes a lot of sense, but it's pretty hard to come up with. Like if you've never seen this before, definitely not something I would come up with for sure. So this is O1. So technically, actually, technically, I think this is actually not O of 1. So this is not a loop, but this is, so when you do a bitwise and, it's still logarithmic because you have to bitwise and every single number. So actually, this runtime is still technically log n, and like this solution is also log n. So technically, these are both log n. But the reason people refer to them as O of 1 is because like there's only 31 bits, so it'll be like log 30 for this or this, which will be basically O of 1. But it's technically not O of 1 regardless. So space here's O of 1. So that's why, like, if you tried this with at least I haven't tried it, but if you tried this with like a really big number, like instead of 2 to the 30, you try it with like 2 to the 1,000 or something. I think this solution and this solution would be roughly, like, obviously this is more operations, so this will still be slower. But as far as like big O complexity, they'll be the same. Because yeah, doing a bitwise and, you have to actually like and this bit and this bit and this bit and so on. There's probably like optimizations for sure to make this faster, but without knowing what those are, it would definitely be log n because you have to check each bit. And yeah, it's going to be all for this one. Hopefully this was helpful. And if it was, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.